Hi. Oh, it's on. Okay. Hi, my name is Mithun. I work on Hive and Catalog in Yahoo. And today I'd like to present some of the work I've been doing sort of benchmarking various versions of Hive within Yahoo. I'd like to present results and learnings and probably go over some tuning tips and so on. About myself, I'm an Catalog committer and a Hive contributor. I've worked mostly on the MetaStore, the notification side, integration with Uzi and stuff like that. I am also frequently distracted by other things Hadoop related at Yahoo. That's usually when my manager's not looking. She's not here. Okay. So let's move on. On the menu today, we're probably going to go a little bit over the data processing use case within Yahoo at Yahoo scale. We'll cover the benchmarks we chose to measure the performance of Hive. We'll go over how things were set up, how I prepped for the tests, and how I ran them. And then we'll analyze the results. We'll take a look at the lessons we learned on the way, and probably at the very end, engage in gentlemanly fisticuffs, otherwise known as Q&A. So let's talk a little bit about the Yahoo grid. The Yahoo grid consists of 16 clusters running Hadoop 23 or Hadoop 2.0. It spans 32,500 nodes, and we process about 750,000 Hadoop jobs every day. That corresponds to between 20 and 25 million Hadoop jobs a month. We're running Hadoop 23, like I mentioned. Our data sets tend to be huge. The data ingestion service that we use indicates that we have 2,000, maybe 2,200 data sets. And those are at varying frequencies. We have daily, hourly, 5-minute feeds, and so on. Now, that corresponds to oftentimes terabytes of data corresponding to a single date partition, and thousands and thousands of files on HDFS. And for processing, we use Pig 11 in production along with Hive 12. So the dichotomy of data processing within Yahoo is as follows. Almost all of ETL happens over Pig. Yahoo is sort of a prolific user of Pig. It corresponds to about 45% of the Hadoop jobs that we run on our clusters. On the complete other end, we use Hive. A little bit for ETL. There are people who do that, but it's mostly for ad hoc analytics. It's mostly for sort of the BI use cases and so on. And the number of Hadoop jobs sort of launched by Hive is a smaller fraction as compared to Pig, but that's gone up dramatically in recent times. Incidentally, we use, since both Hive and Pig are used to process the same data, we use Catalog for interoperability. That's the uptick I'm talking about. Since December of last year, we have gone from a relatively minuscule number all the way to 10% of 25-ish million Hadoop jobs every month. I could say, for the most part, it's either analytics or BI use cases that are driving this. Someone has actually let slip now to our users that it is now possible to connect Tableau, MicroStrategy, Excel, and so on over ODBC to the data on the grid directly. And as romantic as that sounds, it does pose challenges for us. for one, the security team in Hive, in Yahoo, is absolutely convinced that someone in Yahoo is going to copy financially sensitive data onto their laptops and then sort of leave it at a bar as they negotiate their way home in the evening. This is an actual concern. So that brought on ACLs and access control, security stuff, encryption over the wire, encryption on disk, and so on. Second, we have this bandwidth problem where when someone connects Tableau to Hive Server 2, Tableau tries to download all the data in the table at one go. And that could be like terabytes and terabytes of data over a very thin pipe. And that hopefully errors out. And the third problem is probably what gets most press, which is query latency. Now, I've given a couple of examples. We'll only be drilling down into one of these. Query execution time, Hive on MapRed tends to be slow. We know this. Second, Hive tends to do optimizations, and those optimizations might involve things like querying all partitions metadata into memory at one go. And we have seen at Yahoo scale with millions of partitions in a table, that's going to take time. So there's that query latency. And finally, you have the latency caused by bad queries from things like Tableau. Tableau, in order to discover schema for a table, it does a select star and then closes the connection, which is a bit brain dead if you think about it. But that sort of thing brings our systems grinding to a halt as well. So of the three, I would like to actually drill down into query execution time. We needed a benchmark with which to measure the fact that Hive, as it progressed from Hive 10 through Hive 13 on Thais, we have performance sort of heading in the right direction. And the benchmark that we chose for this is TPCH. Now, the Transaction Performance Processing Council, inexplicably abbreviated to TPC, has published a couple of benchmarks. There's TPCDS, TPCH, and maybe a few others. Hortonworks has published their numbers with TPCDS. We figured we'd run TPCH for complementary coverage. That and the fact that the TPCH queries have already been transcribed to the SQL dialect in Hive by other people. The queries that I'm running are actually derived from Reynolds Shin's work. He's the shark guy. And his work was actually derived from a Jira that was posted on Hive. I think it was Hive 600. So my query is sort of derived from there. I just adjust things like map reduce input split size and so on to match the mapper size. So anyway, this is the relational diagram of the tables involved in TPCH. 22 queries spanning 8 tables. The two tables, line item and orders in the top right, those are the big fact tables. Those are the ones that will likely be streamed in the case of a broadcast join. And the two tables at the bottom, nation and region, those are extremely small. Those will be the small tables in a map join. And the other tables are sort of in between these two extremes. The setup. Now, luckily, I had at my disposal a 350-node cluster consisting of, each one had 16 processors, 24 gigs of RAM, so not a whole lot, and 6 hard drives. Which brings me to an interesting tangent. When I first deployed Hadoop to this cluster, it turns out that per node, it was using 4 disks instead of 6 for both HDFS and MapReduce intermediate write. Now, we toyed with the idea of, rather than to expand HDFS and MapReduce to use all 6 disks, we considered keeping them separate. So we ran HDFS on 4 and MapReduce intermediate output on 2. I don't have extensive readings on this, but the idea was that the HDFS throughput does not trample on the requirements of MapReduce. If someone would like to experiment on that front, please talk to me after the talk. Back to the show. RHEL 6.4, JDK 7, 64-bit mode, Hadoop 23.7 at the time, and 2.3. Thales 3, which was the trunk version. And I haven't mentioned this, but Hive 13, which was also a trunk version at the time I ran this. And then I downscaled that cluster down from 350 nodes to 100 nodes. And we'll go into why we tested that, depending on whether you ask the right question. So prep. TPCH ships with a program called dbgen, which produces text data in pipe-separated, new line delimited form. But in production, no one's going to run against text, and if you do, there's something wrong. So I used Hive to transcode this data from text to RC file and awk. Second, I did partition the data. I didn't okay, let me take a step back. We decided we'd test in 3 different sets. We were going to do this with a 100 gig data set total, 1 terabyte, and 10 terabytes. Now, Gopal Vijayaraghavan from Hortonworks, he actually has a MapReduce script with which you can sort of generate different data sizes using this dbgen tool. So that's pretty much what I used. So in the 100 gig case, I did not actually partition the data because the partition keys that I chose had a cardinality of 2500-ish, so you would get way too thin partitions. Hold on to your question. We'll come back. In the 1 and 10 terabyte cases, I actually did do the partitioning. The scripts for all of this are available in a GitHub link that I will post on the second last slide. And finally, the awk stripe size that I used was 64 megs. Now, this is crucial for some of the performance tests towards the end, and I'll explain when we get to it. What follows will be the bunch of graphs corresponding to the results at each of these sets, at each of these data sizes with various versions of Hive. There might be anomalies in these tests, and I left them in the spirit of openness. Hopefully, I can point these out to you before you spot them. This is the graph for the TPCH 100 gig set. If you can't read this, the long blue lines correspond to Hive 10 running on text. At the other extreme of each set is a small sort of turquoise bar that you probably cannot see. And that is actually a good thing. So on the x-axis, we have the various queries, 1 through 22. And on y-axis is time taken. Here's the summary. In case you couldn't actually read this, 18x speed up compared to Hive 10 running against text. But that's sort of like kicking a puppy. No one runs against unpartitioned text files. So the second one is probably a little more relevant. Nearly 12x performance speed up, average, that lies between 5x and 30x, as compared to Hive running RC file, which is a little more representative. The average query time, 28 seconds. The best query time was 5 seconds for Q6. And here's the kicker. 85% of the queries that were run completed in under a minute. This is the 100 GB case. The 1 terabyte case, we begin to see anomalies. It's not so much an anomaly as we begin to see long reduced tails in query 21. Now, if you look at query 21, you'll see this, you'll kind of sort of see why. What I landed up seeing during the test was that there was a long reduced tail in every version of Hive that I tried, including with Thales. That has actually since been resolved. I haven't run my test since. So the summary in this case, over 6x performance improvement with Hive, Thales, org file, as compared to Hive 10 RC file. And that lies anywhere between 2.5x and 17x. Average query time, including the errant query 21, is 172 seconds. And that is down from the 729 in Hive 10 RC file. Over 60% complete in under 2 minutes, over 80% in under 4. I'll move on. The 10 terabyte case, you will spot the anomalies clearly. And in case you don't, the second last set of bars you'll notice, the query, that really is a long reduced tail. And it's hit everyone, including Thales. The second is query 5, that is the fifth set of bars. You're probably going to see that Hive 13 actually has a long reduced tail and the others don't. Now, this could be a result of a couple of things. For one, I had to reproduce the data for Hive 13 because it was on Hadoop 2, as opposed to everything else which was tested on Hadoop 23. So there could have been a change in distribution. It could well just be a bad plan. Once again, I'm told this has actually been resolved in the branch version of 13. But if you look at the other queries, it's almost impossible to see the Thales lines, the turquoise bars at the end. Summaries here, on average, including the errant queries, 6.2x% performance improvement. Anywhere between 1.6 and 10. Average query time, 908 seconds. But if you discount the errant queries, less than half of that. This is as opposed to the 2,100 and whatnot seconds you require for Hive 10. Once again, 60% of the queries complete in under 5 minutes, 71% in under 10 minutes, and query 6, the fastest one, completes in 12 seconds. So that's 5 seconds for 100 gigs, 5 seconds for 1 terabyte, and now 6 seconds for, 12 seconds for the 10 terabyte case. Let's go over, let's see if we can try to explain these speedups a little bit. Let's discount the fact that Hadoop 2 is likely faster than Hadoop 23. If I had to point at one thing, it's probably Thales. Incidentally, if you want to know the details of how Thales does this, there is another talk going on right now. But don't go. You've already heard that Thales allows you to express the physical plan as an arbitrary DAG, which means you can have map, reduce, et cetera. You've heard this story. You've probably also heard that the data is passed between subsequent tasks without incurring the cost of three-way replication on HDFS. You probably know this too. Let's go over a couple of things that probably haven't been called out explicitly yet. I guess the most impressive thing was probably the combination of container reuse and scheduling, the really smart scheduling that Thais can do. So let's consider that there are two stages, and one stage has written data out, and we're waiting for the second stage to consume that data. Now, Thais is actually smart enough to be able to schedule that, the downstream task on the same node, which means the data that has been written out is not being read across the network. Now, that's impressive in itself, but now consider the effect with container reuse, which means that it's going to be doing this within the same JVM, which means it is likely to schedule that task within the same JVM, which means it is going to be reading it pretty much from buffer cache. In other words, the data will probably be read out from the same virtual address as the task that wrote it out. So that's a tremendous performance improvement. A couple of other things, I'm not entirely sure whether that pipeline job startup has gone in, but one of the cool things about Thais is during split calculation, as it figures out which tasks are supposed to start running, rather than to wait for split calculation to complete before launching the job, Thais actually does the smart thing of scheduling those splits that have already been figured out while split calculation is going on. And pipelining that really speeds up the startup time for a query. I could go over other stuff. If we look at Hive, there's two things to call out in what Hive does. The first is statistics. We have table level as well as column level statistics. So things like count star without too much of a predicate returns in constant time, because it's just a fetch from the meta store. So that kind of thing is fast. And the second thing, again, is vectorization. If you, to put it in brief, vectorization involves processing data on a per column, in a per column form by eliminating code that does things like, that puts layers in between, like object inspectors and so on. So because the code that processes it is so tight and so small, at least the design goal is for that code to fit neatly on the processor's instruction cache and just have the data flow through it. This is the idea at some point. It'll probably even get there, but I ran some numbers by turning this on and off as well. I'll share those in a minute. The awk file, if I had to call out one thing, it is predicate pushdown. And we'll cover that in a couple of slides to come. This is with, there's two bars here. This is with the 1 terabyte data set running on Hive 13 Thais with and without vectorization. Barring a few outliers, vectorization on average performed at 1.2x with vectorization disabled. This is at least what I've seen. I'm going to move on. Let's talk a little bit about the awk file, the optimized RC file, jokingly called Owen's RC file format. Does a lot of things that RC file does and then takes it to the next level. So data is, it continues to be stored in columnar form. but other stuff has been added on top. For example, corresponding to row groups, you now have indexes which keep track of the maximum and minimum values for each of the columns in the row group, which means if you have a predicate that chooses rows based on a value predicate, that can be checked against the index rather than checking it against the deserialized values. So you could choose to skip entire groups of rows based on just this, provided you sort your data on those columns. Let's take a step back. The org files are arranged in stripes on disk. And each stripe will have row groups and indexes and so on, and then you have a footer at the bottom. One of the cool things about org is how configurable it is. The table at the bottom indicates the things that you can twiddle with to adjust org file performance. I do have numbers after twiddling a couple of these things, and I would like to go off on a tangent here. Org compression, I've tested with zlib as well as uncompressed. The numbers I can share in the next slide. But I would like to talk a little bit about the org stripe size. By default in Hive, at least at the time I looked at it, the org stripe size was, by default, 256 megs. Remember that the HDFS block size that we were running our benchmarks with was 128 megs, which means if you have a full org stripe, it is, at default, going to span multiple blocks, probably 2 blocks, and will likely be split across 2 different data nodes. The thing about the org stripe is that it is indivisible, which means you need one mapper to consume an org stripe, which means at default, with a 128 meg block size, the mapper is going to read half the stripe locally and the rest of it across the network by default. So, which is why one recommendation is probably to adjust the org stripe size to a value smaller than a block. I would actually say half the block size as a rule of thumb. OK, another tangent. This is something that Gopal kind of pointed out maybe a month ago, which is that if you are copying org data between 2 clusters, and those clusters have different block sizes, then you have to be sure to preserve the block size when you do a discp. Because if you don't, all these calculations and any padding that org adds, et cetera, all that stuff gets messed up. So, so bear those 2 things in mind. I'll move on. This is the effect. This graph is for the effect of compression when turned on and off in the 1 terabyte case. This is, once again, Hive 13 running on the 1 terabyte case on Thales with org files compressed with zlib and not compressed at all. And overall, we see a 1.2x performance improvement if it is uncompressed. This is the 1 terabyte case, and it kind of makes sense because you're not losing CPU cycles trying to decompress the data. The eye-opener was what happened in the 10 terabyte case. I've excluded Q21 here because it skews the rest of the graph and it's not really relevant. But in the 10 terabyte case, one sees that any savings that you gain from not having to decompress the data, you are actually losing because of disk read. Because uncompressed, the data is so huge that it takes that much longer to read off disk. So the performance in this case, on average, swung to 0.95%, the 0.95x the other way. So in the 10 terabyte case, uncompressed actually performed not as well. This is a summary of the of what I just mentioned. The aux type size, half the block size, the tangent about DCP, et cetera. Or compression, you really want to run your own benchmarks before deciding whether to turn on or off by default. We're currently setting it on unless we see otherwise. So the default for us is zlib. I would also mention that one really ought to use Hive merge mapred files and Hive merge map files set to true. And the reason for that is if you don't, you're going to likely land up with a large number of small files on your HDFS per partition. And that increases name node pressure, and that's something we're sensitive to at Yahoo. By doing this, Hive knows to merge this, the small files together to produce the larger files so that your aux type size settings, et cetera, take effect and make sense. Naturally, your mileage will vary, so please do run your own tests. And finally, this is a comparison of performance of the 1 terabyte case between, let's see, this is between the 350 node cluster and a 100 node cluster. The idea was simply to see whether we're going to see 3.5x performance drop. And in truth, the 350 node cluster performs at 1.1x that of the 100 node. This is on average across all the queries. There are a couple of outliers here as well. The reason for why we had to run this again at 100 nodes, we'll go into that contingent on you're asking the right question. Let's go over conclusions. For the most part, the Y-Grid team is kind of happy with the performance that we're seeing with Hive 13 on Thales. We think it is a step in the right direction. We have seen performance numbers plummet, times plummet, performance actually increase. So we have actually seen that Thales is now beginning to approach, at least in the 100 gig case, you've seen near interactive times. Performance was one of several factors that we had to consider. Another was that we have an ecosystem in Yahoo that works today. And that consists of Hive and Pig talking to hcatalog and then running jobs using Uzi. This is a set of things that kind of sort of works well for us in production. So it's good to know that components within this ecosystem are taking this performance improvement step. We've seen that Hive 13 running on Thales does scale. In fact, if you go to the Pig on Thales talk, you will probably also see the Pig side of the story. We've seen that Hive continues to be multi-tenant, and that is sort of tremendously important for us given the number of users we have. We're looking forward to a bunch of things that are sort of on the horizon. Cost-based optimization, that is Harish's and John's work, and Julian Hyde's work. We also hear rumor of an in-memory caching solution built on top of HDFS. I believe Cloudera is working on that. That, coupled with what Thales already provides you, I think is going to show tremendous performance improvements. we aren't done. Like I mentioned in the past, well, a few slides ago, we have hit the query execution time problem pretty well. We seem to have things in hand with Taze, but there's other problems to be solved. SQL compliance right now, for example, the TPCH queries did require, at least at the time, transcribing into Hive SQL syntax. And that's sort of like Andrew Lloyd Webber's sort of rearranging the score of Evita to suit the vocal range of Britney Spears. So unfortunately required. Hive 13, though, has cleaned up a lot of this. In addition, there are problems with the metastore and how it doesn't seem to scale beyond a few million partitions per table. This is something we're actually hitting. This is something that is literally keeping us up at night in Yahoo. Better BI tool integration, that's something we're looking forward to working with Tableau, MicroStrategy, et cetera, for in order not to do those brain-dead queries I was mentioning. The reason I chose the skateboarder was that it's sort of a loose metaphor. Notice how his eyes are not on the camera. He's setting up his next trick, and he's not waving at the camera. Similarly, we are not quite done yet. Here are the references. These are the GitHub links that we have the code for. The first is the YDN post that sort of summarizes the findings of mine. The first link in the GitHub is all the queries as well as the data generation scripts that I have used for my tests. The second is Gopal's parallel data generation tool. The third is Reynolds' GitHub. That links, apart from all his work on Shark, the TPCH scripts on which I based mine. And lastly, the Hive Jira from where all the scripts began. With that, I can now pause for questions. Is there any chance you could ask on the mic, please? They're sort of recording this. They asked me to ask you, sorry.
Have you tried adjusting the index strip size? From 10,000 to some lower number and higher number?
No, I actually did not try that. Okay. So the only variation that I did attempt was adjusting the block size as well as
the strip size.
Yeah, I'm sorry, the stripe size as well as the compression.
So I did a test where I gone back to the strip size of 6 MB, and it was performing better than the half the block size ratio.
Right.
My block size was like 512 MB.
Yes, there are. That is almost expected because what you're seeing there is an increase in parallelism.
Yes.
Yeah, by all means do. I mean, you'll have to find the point at which it makes sense not to reduce anymore.
Okay, and you spoke about the Hive merge functionality of mappers, right, where the OR files are merged. Have you tried bucketing also along with merge, or?
I didn't, well, I should have called this out. The only stuff I did during data generation was partitioning the data. I did not even really sort the data.
Okay.
All that will actually drastically improve performance. I just wanted to keep this even because I don't intend to bucket the data, at least for the foreseeable future, because bucketing introduces possible baggage in the future. Because you will land, that's how you have bucket zero problems, where which have skews. That's where you would put all your records that don't fall into any other bucket.
Yeah.
So part of the reason why I really didn't go into bucketing. But if you look at the Hortonworks numbers,
Yeah.
they actually show how that improves performance.
Okay. Thanks.
Hi, when you scaled from 350 to 100 nodes, what was the file size?
No, the files were identical. So what
Yeah, but you showed like 1.5% change in the performance.
the file size remained identical. All I changed was the amount of compute and the number of data nodes that we had on the cluster.
Okay, because we're finding like when you do scaling experiment across nodes, if your file size is let's say 1 TB and you have a huge amount of nodes, they're not going to scale because you don't need that many.
Oh.
No, you don't need that node. There's a lot of stragglers and
Right.
copying
Actually,
across.
if you really look at it that way, perhaps even 10 terabytes is probably too small for this cluster.
That's exactly
Right.
what
So
I'm saying.
so all I did with, had I the time, I would have actually liked to hit this at a scale larger than 10 terabytes in order to actually truly load the cluster.
Or maybe scale lower and see a linear, if you have a linear section in your, I mean, you keep scaling lower, maybe 50.
True,
20.
that's probably something, the next time I run this,
Yeah.
I should probably look into that. The main point of scaling this down to 100 nodes, the thing I did after that was to run the HDFS balancer to make sure that all the blocks are sort of properly distributed so that you don't have hot pockets.
Okay.
So yeah. But thank you. That's something we should look at.
Hi. When you run the benchmark, is that the only thing that's running on the cluster? Meaning each query, the runtime that you get is implies that there's nothing else running on the cluster at
Yes,
that time?
that is correct.
So how did you account for the multi-tenancy aspect and the challenges in a real-world cluster?
The multi-tenancy is not something that
In
was
the-
part of the benchmark.
Okay.
So, but we do run Hive in production today using Hive 12 on MR, and we've been running versions of Hive since 9. So we have seen that it suits the multi-tenancy use case at Yahoo. I've not tested the Thales thing,
So
but
when
we are running Hive 13 on Thales in Sandbox right now.
Have you noticed a significant difference between the time that you get when you run these things just by themselves without anything else running versus in a real-world cluster when you have a bunch of things contending for resources?
Good question. I haven't measured that.
Okay. The other thing is, have you considered, instead of using TPCH, creating your own benchmark that more mirrors the characteristics of Yahoo?
Yes, we actually did consider that. The reason we landed up with TPCH was primarily that it was sort of industry standard, and we had other benchmarks from, shall we say, competing solutions that we could compare with.
I see. But how useful is it in, like, how accurately does it reflect the actual needs of Yahoo's?
Okay, we did run the TPCH queries by the actual data owners who, the chaps at Yahoo who actually own the data. And they kind of sort of agreed that it was, even if it doesn't cover 100% of the use case, it was representative enough to make a platform decision.
Okay, thanks.
Sure.
So I'm sorry.
Go on.
It's too loud. I'm mostly interested in some other metrics. So you reported the elapsed time. So usually it seems like there's another bottleneck in the system. So did you look at metrics? I'm sure you did, like CPU utilization, network I/O, and disk. I'm wondering in case of, let's say, going from 100 to 350 nodes or from 1 TB to 10 TB, what was the CPU utilization or area under the curve for CPU for each?
Well, actually, that could well have been part of the benchmark. Again, it really wasn't. All we were looking at was query execution. We could have gotten that by doing monitoring on the clusters during that time. We just didn't as part of this run.
Right. I think another measure would have been also concurrency, because if there's some kind of bottleneck happening that allows all queries to take a certain time, maybe if run 10, they will all come back at the same time, and then when you measure effective throughput, compare 100 versus 350 machines, ideally 350 should give you more throughput.
Right. I would actually expect that. I would actually expect at least disk throughput will probably be faster because you have less chance of sort of hot nodes and so on.
Right. Okay. Thanks.
Hi. If I remember correctly, on the dashboard that shows benefits of vectorization, there are some queries that run slower on in vectorized mode.
Yes.
And can you elaborate a bit more why they can be slower?
I'm not entirely sure. You're the Spotify guy.
Yes.
Okay. Right. So I'm not still entirely sure where the slowdown came from. At the time I was running the test, this was off of trunk. Mm-hmm. So we actually saw in places that the combination of PPD, TASE, and vectorization, sometimes the queries would not complete. We did have some stability issues. I marked that down to that. It's probably a corner case that is not being handled well. But again, yeah, I'm not entirely sure yet. One thing that is warranted right now is probably a rerun after Hive 13, the branch has actually stabilized. I haven't actually done that. I think your test might have happened right after. I'm not sure.
Yes, so I did a test on Hive 13, test 0.5. And in my case, I saw benefits of vectorization in case of my query when processing very large data set. But in my case, I used a map join that is not fully vectorized right now. So it was like
okay, I think by default I had enabled map joins.
So in map join, there is still some place when you switch to row mode, but there are some places where you use vectorized mode. So this is why it's only partially supported. And
right.
maybe this is why I have seen like harder to explain numbers.
That could well have been because when I did run the test, I had map join enabled. That could have been part of the thing, but I can't be completely sure. If you see the queries results, you might actually see that I don't have numbers for some cases where vectorization was enabled. And that was, again, chalked down to stability at the time.
Mm-hmm. Okay, thank you.
Sure.
And did you actually run all of your tests on top of Yarn and Tez, or did you attempt to run Hive on just the older API?
I ran Hive 10, 11, and 12 on MapReduce.
So it was only 13 running on the Tez, right? On top of Tez.
Yes, I mean, Hive 10, 11, and 12 do not support running on Tez.
Yes, I do know, just it wasn't so obvious from your slides there.
Okay, I'm sorry, I probably should have made that clearer. It's only Hive 13 and onwards that supports running on Tez. So,
but did you run Hive 13 as well on the older APIs?
Yes, I ran Hive 13 on MR as well as on Tez.
And
performance was, yeah, Tez just blows it away.
So basically you even didn't include this in the slides because it was so much more better than it wasn't even worth including this, right?
It should actually be there.
It was there. I'm sorry if I missed that.
Okay. The line just before the line that you couldn't see was
okay,
that one.
Thank you.
How was your network architecture look like? Just in the slide, I don't see that. I'm
not sure I can explain. I'm not sure I'm qualified to answer that. I could get you in touch with one of our grid ops guys who can answer this for you better than I can. So how about right after? I'll see if I can hunt him down, assuming he hasn't run away.
Okay.
I just have one question. We know that partitioning is good, obviously. We don't have to read through all the data. Have you seen that going to ORC has diminished the need to partition in certain cases, since you don't have to scan through all that data now?
All right, between you and me and the camera, we have this problem right now. We actually have a table, a secret project going on within Yahoo that is producing 10,000 partitions every hour, 250,000 partitions every day within the same table. We have 5 levels of partition. So there is probably such a thing as too many partitions, or at least that's the point I'm trying to make, which is if we were, instead of using these as partition keys, if we knocked off, say, one of those partition keys and converted the data to ORC and then sorted based on that, you could use the index filters, that is predicate pushdown, to select only those bits of data that you care about. So that is part of the reason we have this sort of pressure on HCatalog right now. So I would actually argue that, that yes, ORC does provide you a way of getting away from that, but I haven't actually proven that yet with this data set. Okay. I fully intend to as possibly next week.
Great, thank you.
Sure. Is it lunch?